Greetings, everyone. Today, we're going to delve into the fascinating world of analytical data evaluation. Analytical data evaluation is the process of examining and interpreting data to uncover insights, patterns, and trends. Let's explore the key steps and techniques involved in this important analytical process. Our topic outline consists of measures of central tendency, dispersion, uncertainty propagation, confidence intervals, and significance testing. Now, we're diving into the fundamental concept in statistics, understanding measures of central tendency. Essentially, these are statistical measures that help us understand the center or typical value of a dataset. They are crucial for summarizing data and gaining insight into its characteristics. The three most common measures of central tendency are the mean, median, and the mode. Our first stop is the mean, often referred to as the arithmetic average. It is calculated by summing up all the values in the dataset and then dividing by the total number of values. There are two types of mean, sample mean and the population mean. The sample mean is mainly used to estimate the population mean when population mean is not known as they have the same expected value. Sample mean implies the mean of the sample derived from the whole population randomly, while the population mean is nothing but the average of the entire group. Let's explore a scenario where statistical analysis is used to understand blood sugar levels in hospitalized patients. A total of 25 patients admitted to a hospital are tested for levels of blood sugar, and the results obtained were as follows. Find the mean of the above data. First, add up all the blood sugar values obtained from the test, which is equal to 1,891. Next step is to determine the total number of patients tested, which in this case is 25. To calculate the mean, divide the sum of the data values by the total number of patients, which will give us 75.64. Therefore, we conclude that the mean blood sugar level of the 25 admitted patients is approximately 75.64 milligram per deciliter. This value represents the average blood sugar level across the patient population tested. By following this step, you can calculate the mean blood sugar level and interpret the result in the context of the sample data provided. But take note that the mean is sensitive to extreme values, also known as outliers, as it takes into account every value in the dataset. Therefore, it may not always accurately represent the center of the distribution if the data is skewed or contains outliers. Next up, we have the median, a robust measure of central tendency. Unlike the mean, which can be influenced by outliers, the median represents the middle value of the dataset when arranged in ascending order. If n is odd, median is equal to n plus 1 over 2. If n is even, median is equal to n over 2 plus n plus 1 over 2 all over 2. Note that n is the number of values in the dataset. It is not affected by extreme values or outliers, and it is often used when the data is skewed or contains outliers. For this example, in order to calculate the median, suppose we have the data below. First, we need to rearrange the data into order of magnitude. Our median mark is the middle mark. In this case, it is number 56. But what happens when you have an even number of scores? We rearrange again that data into order of magnitude. Only now we have to take the fifth and the sixth score in our dataset and average them to get a median of 55.5. Now, let's explore the mode, which signifies the value that appears most frequently in the dataset. This measure offers insight into the most prevalent values, highlighting potential patterns or trends within the data. Note that it is possible to have no mode, one mode, or more than one. In the ungroup data, the mode is the most frequently occurring value in the dataset. Meanwhile, for the group data, it is the data that are given in the form of range rather than distinct number. It is mathematically represented as mode is equal to L, or the lower limit of the data, plus f sub 2, which represents the preceding class frequency, plus f sub 1, or the modal class frequency, divided by 2 times f sub 2 minus f sub 1 minus f sub 3, or succeeding class frequency, times n, the population size. It's crucial to understand the nuance and differences between these measures. In conclusion, measures of central tendency serves as invaluable tools in data analysis, offering insights into the core of the characteristic of dataset. By understanding their equation, application, and limitation, we can make more informed decisions and drive meaningful outcomes across diverse domains.
Hi, I am Sherlyn K. Uy, and now I'll be discussing about measures of dispersion. As discussed from the previous topic, The measure of central tendency pertains to the measures of the center of a distribution of scores. Meanwhile, here, the measures of dispersion or the measure of variability describes the spread of scores in a distribution, wherein the more spread out the scores are, the higher the dispersion or spread. As you can see here in figure 1, the y-axis is the frequency and the x-axis represents values for a variable. There are two distributions here labeled as the small and the large distribution. You can see that these distributions are normally distributed and the mean, median, and mode for both fall in the same point. What is different between these two is the spread or the dispersion of scores. The taller looking distribution shows a smaller dispersion, while the wider distribution shows a larger dispersion. For the small distribution here in figure 1, the theta values are concentrated closely near the mean, while the large distribution, the values are more widely spread out from the mean. There are two types of measure of dispersion. First, the absolute measure of dispersion consists of the same units as the original set. Next is the relative measure of dispersion, which is independent of units and is expressed in ratio or percentage. Today, we'll be focusing on the four main methods of measure of dispersion, such as the range, interquartile range, and the quartile deviation, mean deviation, standard deviation, and the variance. The range is the simplest measure of variability to calculate and one we all probably encountered many times. The simplicity of calculating range is appealing, but it can be a very unreliable measure of variability as it is highly influenced by outliers. Range can be calculated by simply getting the difference between the highest and the lowest value from the dataset. Meanwhile, the coefficient of range can be solved through getting the ratio of the difference between the highest and the lowest value to the sum of the highest and lowest value of frequency. As an example, listed in the table are the scores obtained by the students in their exam. To calculate for the range, first is to identify the highest and the lowest value in the dataset. Here, the maximum value is found to be 49 and 12 is the minimum value. Subtracting these two will give you 37 as the range for this dataset. Meanwhile, the coefficient of range can be calculated by dividing the difference between of the highest and lowest value to its sum. Hence, here the answer is 0.621. To identify values in terms of quartiles of the distribution, interquartile range deviation is used. This pertains to the range of the middle 50% of the score in the distribution and is sometimes used to communicate where the bulk of the data in the distribution is located. And to solve this, simply get the difference of the third quartile or the upper quartile and the first quartile or the lower quartile. As an example, let's find the interquartile range of this data. To solve this, first is to arrange the values in order of increasing value. In this example, the values are now arranged from lowest to highest, which is 36, 42, 48, 49, 52, 54, 67, 71, and 74. Next is to locate the median. Here in the example, 52 is the median. Then, separate the scores into first and second half. Next is to identify the Q1 and Q3. And to identify this, for even numbers, simply get the mean of the middle values of the set. And for the odd numbers, the median for the set is considered as the Q1 and Q3. Here in this example, contains an even numbered score, hence the means of their values will be calculated. Next is to calculate the value of Q1 and Q3. Remember, you will only do this if the number of values in your dataset is even numbers. So for Q1, the middle values for the first half are 42 and 48, and getting the sum of this divided by 2 is 45. While in Q3, 67 plus 71 divided by 2 is 69. Once you get the values for quartile 1 and quartile 3, you can now subtract them. Here in the example, quartile 3 is 69 and quartile 1 is 45. Then 69 minus 45 is 24. Now your interquartile range is 24. Quartile deviation, on the other hand, is the half of the distance between the first quartile and the third quartile. Its coefficient can be solved by getting the ratio of the differences between the Q1 and Q3 to the sum of Q1 and Q3. As an example, we know that the Q1 and Q3 from the previous example are 45 and 69. From this, we can calculate the quartile deviation. So 69 minus 45 divided by 2 is 12. Then for the coefficient of quartile deviation, 69 minus 45 over 69 plus 45 equals 0.21. Variability can also be defined in terms of how close the scores in the distribution are to the middle of the distribution. Using the mean as the measure of the center of the distribution, we can see how far, on average, each data point is from the center. Remember that the mean is the point on which a distribution would balance. We can examine spread by identifying how far each value is from the mean, and this is known as the deviation from the mean or the differences from the mean. The sum of the deviations is the smallest for the mean value, and interestingly, the sum of the deviation from the mean is 0 because the mean is the fulcrum of our balance point. In the formula, the value is represented as x, deviation from the mean or the deviation from the median is the x minus mean or x minus median, and n is the number of values in the dataset. As an example, here in the table, the x values or the score values are 27, 22, 26, 33, 36, 29, and 35. And getting the mean score is 29.7 and the median is 29. All the x values will be subtracted to the mean or median, hence is columns 2 and 3. For the x minus median, the values were negative 2, negative 7, negative 3, 4, 7, 0, and 6, and its sum is 5. For the x minus the mean or the deviation from the mean, the values are negative 2.7, negative 7.7, negative 3.7, 3.3, 6.3, negative 0.7, 5.3, and the sum is 0.1. Calculating for the mean deviation from the median, simply divide the total value of the x minus the median over n. Here, the x minus median is 5, and the n, or the total number of values from the set, is 7. And 5 minus 7 equals 0.71. Then from this, we can calculate the coefficient of the mean deviation from the median by simply dividing the mean deviation over the median. Hence, 0.71 over 29 equals 0.02. Similar steps are done with the deviation of the scores from the mean. First is to subtract all the x values to the mean and get its total. Here, the total value of x minus the mean is 0.1. Then, to get the mean deviation from the mean, simply divide that value to the total number of values in the dataset, which is 7. Then 0.1 over 7 is 0.01. From that, you can get the coefficient of mean deviation from the mean by simply dividing that MD to the mean. Here, 0.01 divided by 29.7 as the mean, you will get 0.003. On the other hand, the variance is defined as the average squared difference of the scores from the mean. The mathematical definition of the variance is the sum of the squared deviations or the distances of each score from the mean divided by the number of scores in the dataset, and it is represented by sigma squared. On the other hand, the most common measure of variation or spread is the standard deviation. It is a number that measures on average how far data values are from the mean. The standard deviation provides a numerical measure of the overall amount of variation in the dataset, and it can be used to determine whether a particular data value is close to or far away from the mean. It can be solved through getting the square root of the variance. Moreover, its coefficients is calculated by getting the ratio of the standard deviation and the mean value. As an example, the given data contains the x values such as 78, 65, 78, 76, 68, 81, and 64. Getting the mean value for this, you'll get 72.9. Then subtract the x values to the mean, you'll get 5.1, negative 7.9, 5.1, 3.1, negative 4.9, 8.1, and negative 8.9. Then square this, you'll get 26.01, 62.41, 26.01, 9.61, 24.01, 65.81, 20, and 79.21. Getting the sum of this is 292.87. The variance is calculated by dividing the total value of the square deviation of the scores from the mean and the total number of values in the defect. So 292.87 divided by 7 is 41.8, and getting the square root of this value will give us the value for our standard deviation. Then square root of 41.8 is 66.47. Lastly, the coefficient of the standard deviation is the quotient between the standard deviation and the mean value. So 6.47 divided by 72.9 is 0.09. That would be all, and I hope you learned something from me today. And to check your understanding, you can answer this example. Thank you.
Good day everyone, I am John Pico Palmero, and in this section, we're going to discuss the uncertainty propagation. Uncertainty propagation is a statistical calculation used to combine the uncertainties from multiple different variables or measurements in order to provide the accurate measurement and its uncertainty. It also allows us to estimate the expected uncertainty for an analysis. It also helps in deciding how to improve the uncertainty in an analysis. It can also be used to decide which procedure must be chosen to be used in order to provide the smallest overall uncertainty to ensure the accurate results. So in this discussion, symbols will be used in the equations involved in this topic. The letter R refers to the result, while the letters A, B, C, and onwards refer to the measurements, such as the volume or any quantity that can be measured. The symbols S sub R refers to the uncertainty of the result, while the symbols S sub A, S sub B, and S sub C refers to the corresponding uncertainties in the given measurements. Using the uncertainty propagation involves different mathematical operations. The first is the uncertainty when subtracting or adding measurements. In these operations, the absolute uncertainty of the result can be calculated by taking the square root of the sum of the squares of the absolute uncertainties of each individual measurements. Let's use this equation by solving this sample problem. The Class A 10 milliliter pipette is used to deliver two successive volumes. Calculate the absolute uncertainty for the total delivered volume. We can see that we have the table of data for the volume delivered by the Class A 10 milliliter pipette. Since we are asked to calculate the absolute uncertainty of the total delivered volume, we must first get the mean from the given data. Using the data for the mean, the sum of all data over the number of trials is equal to 9.992 milliliters. So this is now the mean of the data given. After calculating the mean, we will use it to calculate the standard deviation, which is equal to 0.006. Now that the mean has been previously calculated, and since the problem mentioned that the pipette delivered two successive volumes, we will calculate the total volume by adding the mean by itself, which will be equal to 19.984 milliliters. Now that we have calculated the total volume, we will use the calculated standard deviation to get the absolute uncertainty through the use of the equation of uncertainty for addition and subtraction. Substituting the values for the equation, the absolute uncertainty is equal to 0.0085 or 0.009. Therefore, we can report the answer as the 19.984 milliliters with a margin of error of plus minus 0.009 milliliters. Other than the addition and subtraction, the uncertainty propagation can also be used even when the measurements are multiplied or divided. The propagation of uncertainty is equal to the square root of the sum of the squares of the uncertainties for each individual measurements. So let's use the formula for the following sample problem. The electric charge Q passing through an electrical circuit is equal to the product of current in amperes and time in seconds. So when a current of 0.15 plus minus 0.01 amperes passes through the circuit for 120 seconds plus minus 1 second, the total charge is 18 coulombs. So calculate the uncertainty for the total charge. The given measurements are the current of 0.15 amperes with an uncertainty of 0.01. The given time is equal to the 120 seconds, and the given result is the quantity of charge, which is equal to 18 coulombs. Since the charge is a product of the current and time, we can use the uncertainty propagation for multiplication or division. So using the formula of uncertainty propagation, we will substitute the given measurements, which are the current and time, and calculate them in order to get the relative uncertainty, which is equal to positive negative 0.0672. So to get the absolute uncertainty of the result, we will arrange the equation to be equal to only the uncertainty of the result. Substituting the values and calculating it will yield the absolute uncertainty, which is equal to positive negative 1.2. Therefore, we can report the answer as the 18 coulombs with a margin of error of plus minus 1 coulomb. Since there are many calculations that both involve addition, subtraction, multiplication, and division, in those problems it can be solved by calculating each operation separately using the corresponding equations. So for the following sample problem, the concentration technique, the relationship between the measured signal and an analyzed concentration is given by the following equation. So we have here the given equation. So calculate the uncertainty for the analyzed concentration if the measured signal is equals to 24.1 plus minus 0.02. The signal for the reagent is equals to 0.96 plus minus 0.02, and the constant K is equals to 0.186 plus minus 0.003 per parts per million. So in this problem, we are asked to calculate the uncertainty of the analyzed concentration, where the given measured signal, or the S sub measurement, is 24.37 with a margin of error of plus minus 0.02. The signal of the reagent is equals to 0.96 with a margin of error of plus minus 0.02. The constant K is equals to 0.186 per parts per million with a margin of error of plus minus 0.003 per parts per million. So to calculate the uncertainty for the analyte, we must calculate the analyte's concentration first by rearranging the given equation. So for solving the concentration of the analyte, we we will get this equation. So C sub A is equals to the measured signal minus the signal of the reagent all over constant K, which will be equal to 24.37 minus 0.96 over 0.186 per parts per million. Calculating this, we will get the concentration of the analyte, which is the 125.9 parts per million. Now that we have calculated the analyte's concentration, the next thing to do is to calculate its relative uncertainty using the uncertainty propagation for multiplication or division. But first, we must need to get the numerators for the equation. So in order to do that, we need to calculate the uncertainty of the numerator using the uncertainty propagation for addition and subtraction. So we have here the equation S sub r is equals to the square root of 0.02 quantity squared plus 0.02 quantity squared. So calculating this, we will get the uncertainty equal to 0.028. So now that the numerator is 0.028, we will use it to complete the calculation for the relative uncertainty. So here, the equation, we have S sub r over r equal to the square root of 0.028 over 23.41 quantity squared plus 0.003 over 0.186 quantity squared. So calculating this, we will have the relative uncertainty equal to the 0.0162. So now that we have calculated the relative uncertainty, we will use this to calculate the absolute uncertainty. So S sub r is equals to 125.9 parts per million times 0.0162. And calculating this, we will have an absolute uncertainty of plus minus 2.0 parts per million. Therefore, the analyte's concentration is equal to the 126 with a margin of error of 2 parts per million. Since there are many other mathematical operations used in analytical chemistry problems, shown in this table are the different equations of uncertainty propagation to the different corresponding mathematical functions. So this is the reference used for the preparation of this presentation. And that is all for this section. Thank you very much for listening.
Good day, everyone. I am Gabriela Monique Albornoz, and I will be discussing about confidence interval. Confidence intervals are statistical tools used to estimate the range within which a population parameter is likely to lie. They provide a measure of uncertainty and are essential in drawing reliable conclusions from sample data. This report aims to explore the concept of confidence intervals, their calculation, interpretation, and significance in statistical analysis. First, let us define what is confidence interval. Confidence intervals measure the degree of uncertainty or certainty in a sampling method. It is a range of values derived from sample data that is used to estimate the unknown parameter of a population. So the formula for a confidence interval is Ci is equals to x positive negative z multiplied by s over the square root of n, where Ci is the confidence interval, x is the sample mean, z is the confidence level value, s is the sample standard deviation, and n is equals to sample size. So for confidence level, the confidence level represents the probability that the calculated confidence interval contains a true population parameter. Commonly used confidence levels are 90%, 95%, and 99%. A 95% confidence level, for example, implies that if the sampling process were repeated numerous times, the calculated interval would contain a true parameter in approximately 95% of cases. When interpreting a confidence interval, it's important to understand that the true parameter is not fixed within the interval, but has a high probability of falling within it. A wider interval indicates greater uncertainty, while a narrower one suggests more precision in estimation. Also, there are several factors that influence the weight of a confidence interval, including sample size, variability of the data, and chosen confidence level. Larger sample sizes generally result in the narrower intervals, as I've said, while increased variability widens them. Now, let us try to solve this problem. Suppose a researcher wants to estimate the average height of adults in a city. A random sample of 50 adults is taken, and their heights are recorded. The sample mean height is 170 cm, and sample standard deviation is 8 cm. Calculate a 95% confidence interval for the true average height of the entire population. So for our given, sample mean is 170 cm, sample standard deviation is 8 cm, sample size is 50, and the confidence level is 95%. So for our solution, for 95% confidence interval, the z-score is approximately 1.96. This value is obtained from standard normal distribution tables or statistical software. So the confidence interval is calculated as follows. First, let us calculate the margin of error, which is E is equals to Z multiplied by S over the square root of N. So we have E is equals to 1.96 multiplied by 8 over square root of 50, which is approximately 2.77. So to get the confidence interval, we must get the sample mean, which is 170 cm minus 2.77, which would result to 167.23 centimeters, and 170 plus 2.77, which will result to 172.77 centimeters. So the average confidence interval would be 95% in the entire population is approximately 167.23 centimeters and 172.77 centimeters. This means we are 95% confident that the true average height falls within this interval based on the sample data. In conclusion, confidence intervals are indispensable tools in statistical analysis, providing a means to quantify uncertainty and make informed decisions based on sample data. Understanding their calculation, interpretation, and the factors influencing them is crucial for researchers. As statistical literacy continues to grow, the proper use and interpretation of confidence intervals contribute to more accurate and reliable conclusions. So that would be all. Thank you.
Hello everyone, I'm Erica Maria Mines, and today I'll be discussing the last part of our presentation, which is about significance testing. So we're going to discuss its definition, steps, and types. To begin, significance testing is a powerful tool that can be used to assess if our claim or hypothesis is true as supported by the data that we have. So during high school, we were taught that there are two types of hypotheses, the null and alternative. The null hypothesis states that there is no significant difference on the data being compared, while the alternative says that there is a statistical difference between them. So it is usually expressed in terms of probability. That's why the graph here illustrates our significance testing. The peak of the curve is where most of our observations will occur. It is inside the set confidence interval. And in significance testing, we can say that our data, termed as the p-value, is statistically significant if it falls outside the set confidence interval. So there are four main steps in significance testing. First is to state your hypothesis. Then, we have to calculate our test statistic. We can use different statistical softwares to do this, or we can simply substitute them to their respective formulas. After that, we have to look at their p-value and compare it to the set alpha value that depends on our field of study. But the researchers usually set 0.05 as their alpha value. So if our p-value is less than the alpha value, then we have to reject our null hypothesis. However, if our p-value is greater than our alpha value, then there's no need to reject it. Now that we are familiar with the basic steps of significance testing, we are going to explore the different types of significance tests and when do we have to use them. So this flowchart contains the commonly used significance tests. Right now, this looks like a huge chunk of idea, but don't worry because we're going to discuss them one by one. In determining the type of significance test that we must use, we have to answer certain questions. First, we have to identify the type of data that we have. We also need to consider the number of groups that will undergo the statistical test, if our data is paired or unpaired, if we're looking for differences or correlation, and if our data are parametric or non-parametric. What does it mean? So when we say type of data, we have the categorical and numerical data. Categorical data are qualitative. For example, a person's shirt size, hair color, or gender. These are non-numerical information that are used to describe a sample's qualities or characteristics. Meanwhile, numerical data are quantitative. They can be measured in numerical values. So there are two types of numerical data, discrete and continuous. Discrete data are those that can be counted. They're usually expressed in integers like the number of eggs in a basket or the number of days in a month. While continuous data can take any numerical value, like a person's height, the wind speed, the water's temperature, and so on. Meanwhile, we also have to consider the number of groups involved in our study. Different tests must be used when we're dealing with one group, two groups, or three or more. Then, we also need to assess whether our data is paired or unpaired. To differentiate between the two, in paired data, each observation in one set corresponds directly to a specific observation in the other set. For example, we're going to record the weight of individuals before and after going through a weight loss treatment. So we have the same subjects that are observed under different conditions, while unpaired data comes from independent samples. Unlike the paired data, there's no link between the observation in one set and the observation in the other. For example, we would like to compare the test scores of section A and section B in general chemistry. After that, we also have to consider if we're testing for our data's differences or correlation. The test for statistical differences helps us figure out whether there's a real differences in the mean of two groups or it just occurred due to random chances. While correlation tells us how closely related two things are. It can be used to see if there's a connection between two different types of information, like height and weight, or whether studying more leads to higher test scores. But we have to take note that correlation does not imply causation. Lastly, we have to consider whether we are dealing with parametric or non-parametric data. Parametric data assumes normal distribution. It fits a certain pattern, while non-parametric data are free from this pattern. It's important that you know the type of data that you have because statistical tests like t-test, z-test, ANOVA assumes normal distribution. Otherwise, you have to use their non-parametric counterpart. So to know whether our data is parametric or non-parametric, we have to conduct tests for normality. Some commonly used tests for normality are the Kolmogorov-Smirnov and the Shapiro-Wilk test. You can easily run them using R or SPSS. Now that we have familiarized ourselves with the common statistical terms, let's proceed in knowing the type of significance tests that we must use depending on the kind of data that we have and the goal that we want to accomplish. Also, I would like to mention that we'll be seeing lots of formulas here, but we shouldn't be overwhelmed because in reality, we don't really compute them manually. We just usually run them in statistical softwares for a more efficient and accurate results. I just included them here for familiarization. And the only important thing here is that we know when to use a certain statistical test. So to begin, we have to analyze the type of our data. If we have categorical data, then we can use the chi-square test. In this test, we need a minimum of 2 categorical variables with 2 or more groups for each variable. Now, if we have numerical data, then we have to ask the number of groups that we're dealing with. For instance, if we only have one group, we can use the student's t-test to check if the mean value of the group is significantly different from our theoretical value. For example, you set the temperature of your room to 25 degrees Celsius using a thermostat. Then you created a thermal sensor that measures the temperature in your room. So you took the readings of your sensor every 10 seconds for 5 minutes. We can use the student's t-test to compare the mean value of our sensor readings to the temperature set in the thermostat. Now, if we have 2 groups, we have to ask first if our data is paired or not. If we have unpaired data, then we can use the t-test for independent samples for parametric data, while the manipulative test for its non-parametric counterpart. Here we can use the previous example about the test score comparison of the students in section A and section B in their general chemistry exam. However, there are 2 types of t-tests. It's t-test for equal variances and t-test for unequal variances. And to know if our variances are equal, we can perform the f-test or the Levene test. So these are the formulas for the independent t-test assuming equal variances, for those with unequal variances, and for the man-meeting use test. This is usually used as an alternative to t-test if our data does not follow normal distribution. Also, I would like to mention the z-test, which functions the same as the t-test. However, their main differences is that z-test is prepared when you have large sample size. Now, what if we have paired data? Well, if our data is paired, we have to ask first if our goal is to find their differences or correlation. Because if we only aim to find the differences of paired data, then we can use the t-test for dependent samples, while the Wilcoxon rank sum test serves as its non-parametric counterpart. The previous example about the comparison of the initial and final weight of the people who went through weight loss treatment fits this statistical test. However, if our aim is to know if the variables in our data has correlation, then we can use the Pearson correlation coefficient for parametric data, while the Spearman's rank correlation coefficient works well for non-parametric data. To give an example, we can use this if we want to test if there is a correlation on the student's number of hours of studying and their general weighted average. The closer our correlation coefficient to 1, the higher the correlation between the 2 variables. And the closer it is to 0, the lower their correlation. Going forward, if we're dealing with 2 or more samples, then we still must ask if the data are paired or not. For unpaired data, we can use the one-way analysis of variance or ANOVA and the Kruskal-Wallis for its non-parametric counterpart. In performing ANOVA, it is preferred to use groups with equal sizes to prevent reducing its statistical power. So here is the Kruskal-Wallis, which is the non-parametric alternative of ANOVA. While the ANOVA's concern is the differences in the group's mean, the main concern of Kruskal-Wallis is the differences in their group's rank total. So the result of ANOVA or Kruskal-Wallis will only show us if there is a significant difference between the groups, but it will not tell us the pair of groups that are statistically different with each other. To identify that, we have to perform post-hoc analysis or post-ANOVA. There are several types of post-hoc tests that can be performed. Some commonly used tools are the von Peroni, Tukey, Shupé, and Duncan. Each of these have their own strengths and disadvantages that you have to consider when choosing the post-hoc test to use. Lastly, if we're dealing with more than 3 groups that have paired data, then we can use the repeated measures ANOVA for parametric data or the Friedman test if our data is non-parametric. A good example of this is when you want to know if there is a significant difference in the cigarette consumption of heavy smokers when they undergo a rehabilitation. You can use 3 time points to observe the cigarette consumption of the same subjects before the treatment, after 6 months, and after 12 months. Then here's the formula for the Friedman test. Unlike the repeated measures ANOVA, this uses ranks rather than the actual measured values. To end our presentation, here's some common statistical tools that we can use for significance testing. I tried my best to comprise this topic, but I feel like there's still a lot left to discuss. So if you have any questions, don't hesitate to send a message on my student account. Thank you!